An integer program is something which looks similar to a linear program, but it has the additional condition that each variable must be an integer. And this is an example of a so-called NP-complete problem. And NP-complete problems are very hard to solve. And there does not exist an efficient algorithm for solving an NP-complete problem with general input. For some special cases, but that's not what we're interested in now. Okay, so instead of trying to find an efficient algorithm, then one bad method would be to enumerate somehow all possible solutions and select one which is best, but that's not very useful because it would take forever. And what we do instead is to use the design paradigm branch and bound, which essentially creates a search tree, and this with the different possible solutions, and tries to limit the size of this tree as much as possible. Okay, and this algorithm design paradigm was invented by Ailsa Land in the late 1950s and at the London School of Economics, and she is now 93 years old. Okay, so let's see how she did this. We start with an integer program. So we say that this is a node in a tree. Okay, and then we use something called a relaxation, and that means solving not exactly the same problem. I mean, not exactly the integer program, but a simpler problem. And what we hope is to get some useful information back. And in this case, we solve the same input, but use simplex. And then with this first node, if we are lucky, then simplex find an integer solution. And then we are done, of course. And if there is at least one variable that's not integer in the output from simplex, say xk, then we can create two new nodes as children from this. And one of the nodes is given, okay, the nodes are get the same inequalities or conditions as the parent, but in addition it gets one of these. So that this variable should be less than or equal to the floor of this value, or in the other branch that it should be greater than or equal to the ceiling of this value. So when we branch and put additional constraints, eventually we will come to an integer solution. It may take some time, but it's easy to see that we will limit the search space and eventually find an integer solution somewhere. Okay. This may look like, so this is the basic idea of creating a search tree and adding constraints from the parent to the newly created children. When we create a child, we evaluate it with simplex at once. So each node has the value of z. Okay. In addition, we remember the best integer solution found so far. In this case, we have not found any. I mean, we can assume that since we have only these three nodes. And the first one was not an integer solution. But in general, we may have found an integer solution during this search. And if we haven't, well, then the first integer solution will be the best integer solution found so far. And the best integer solution found so far is denoted by Z star. Okay, so what should we do to limit this search tree? When we create, we will see that now, when we create this node and solve it with simplex, then if this Z is less than the best integer Z, then there is no point in continuing searching this branch, since it clearly cannot be better than that one. The only thing that can happen is that we will limit the search for this one with additional constraints, and they obviously cannot be better than what we had already found, since this one was worse than that one. Okay, so if this one is worse, then we can forget this part of the tree. Say instead that this one was better than that one, but that it's not an integer solution. Okay, what we will do then is to remember this node. So we take this node and put it well, in a queue or in a list or somewhere. We put it aside for future use. Okay, well, it looks like as if we build this tree, but actually after we have created the two children, we don't need the parent. So this one will be deleted, since we want to save memory. So conceptually, actually it looks better. Conceptually, we create a tree, but once we have created two children of a node, we don't keep the parent, because we have no use for it any longer. The only node that we are really interested in is the node with the best solution. So here we have remembered the best Z, and we remember also the solution for this node. But to save memory, we will remove that one. Okay, so we continue and take a node. I mean, we have a set. In the pseudocode, it's called H, this set. So here we have lots of nodes that we want to explore. And we take a node from H. And so this, we can say, this contains lots of nodes. They are somehow in this set, in some way in this set. Think of it as a linked list. That's the simplest to do in the labs. Okay, and then say in the future we find another integer solution which is better than that one. What should we do then? So say we have a new Z star when we have explored the nodes, and we happen to find an integer solution, and it's better than that one. So we forget that one, and here we get a new one. What should we do then? Answer: we can throw away all nodes in this set with a Z value that is less than this one, because, well, they can never get better than the new best integer solution. So there are two situations when we limit the search space. Either when we created a new child and we evaluate it with simplex and find that the Z is less than the best integer, then we can forget it, as here. Or when we happen to find a new integer solution, then we can remove all, not all of them necessarily, but all with the Z that is less than what we found. Okay, so this is the branch, and removing nodes either like that or like that is bound. Okay, so that's what I just mentioned on this figure. I mean the bound. Okay, so that's basically what you need to understand about the branch and bound. And the pseudocode is in Appendix B, so you can read it. And I can really give you the recommendation that you should keep all data structures as simple as possible. There is really no need to make a fancy data structure for this before your program works. It's always best to make a correct program, and then if you have time, make it a fast program. It's always easier to make something simpler and improve that instead of starting with something complex. Okay.